Hello everyone, I hope you are all doing well. This is Zeshan Shoaib and today I will give you an overview of the article whose title is a GLM-based method for the automatic identification of functional events in fNIRS data recorded in naturalistic environment. Here we can see a brief introduction of this article. This article was published in 2017 in Neuroimage journal, whose impact factor is 7.4, and this journal is a Q1 journal in Neuroimaging category. This article was published by Paula Pinti and his group fellows, and in this article they presented a novel GLM method for event identification of fNIRS data in a naturalistic environment. Means with this algorithm we can analyze the fNIRS data which we recorded using real-world experimental paradigms. In this slide here we can see I will give you just a brief introduction of fNIRS device. fNIRS device is a non-invasive neuroimaging technique. This device use sources and detectors to record the brain activity when the subject performs a particular task. This device measures the oxy and deoxyhemoglobin concentration changes in relation to a particular task in targeted brain region. In recent years, researchers are utilizing this device to know about many social, psychological, and medical related changes occurred in brain to know the functionality of brain. So, due to recent technological advances, functional near-infrared spectroscopy devices can be used to perform neuroimaging in the real world. However, as real-world experiments are designed to mimic everyday life situations, the identification of event onsets can be extremely challenging and time-consuming. In this study, they presented a novel analysis method based on general linear model, least square fit analysis for the automatic identification of functional events directly from real-world fNIRS neuroimaging data. And in this study, they also generated the synthetic data to validate this algorithm and to measure its accuracy. The formulation and the detail of this algorithm you can read in the article. In this presentation, I will only talk about the synthetic data generation because in my point of view, it has many uses and generating the data according to a particular experimental paradigm could have many applications, especially in BCI to train the algorithms or many other study schemes. This slide just showing the basic equation used in the GLM-based fNIRS data analysis, and this is the model as well which is used to generate the synthetic data in this article. So the equation is y is equal to x beta plus epsilon, where y is n by m matrix and n is the number of time points and m is the number of fNIRS channels. So this matrix y is representing the basically measured fNIRS signals, and here the matrix X is a design matrix, and this is a n by w matrix composed by w regressors, and the regressors constitute the model of functional activation and are computed by convolving a box call function with the canonical hemodynamic response function. The detail about the box call function and canonical hemodynamic response function I will show you in the next slides. And here beta indicates the contribution of each regressor to the observed responses, and the epsilon is a n by m error matrix, includes the independent and identically distributed errors. In this slide, I will give you a brief introduction of boxcar function and hemodynamic response function. A boxcar function could be any function which is 0 over the x-axis except for a single time interval where it is equal to any constant. This box function generally represents the events in the experimental paradigm. In this article, to test all the possible combinations of time duration of the events, they created boxcar functions by translating each event onset with 1 second step throughout the experiment, as we can see in figure A. These boxcar functions we can see in is looking in this figure like vertical lines. And for each time location, they increased its duration with 1 second step either until the end of the experiment or until a maximum value that can be set by the user, as we can see in figure B. This means that a hemodynamic response would not be sustained for more than 5 minutes, means from 0 to 300 seconds. Here, each boxcar function corresponding to a certain event onset and duration, and these are convolved with the hemodynamic response function, which we can see in figure C. They choose hemodynamic response function composed by a linear combination of two gamma functions, as we can see below this figure. And in this equation, a positive part is the modeling of the response, and a negative part is the undershoot. But if we want to make any study design, we can define this hemodynamic response function according to our experimental paradigm. So this boxcar function is actually a synthetic presentation of the experimental paradigm. We can also say that this is equivalent to a correlation analysis, as one regressor is tested each time. So briefly, I can say that in this diagram we can we can define the boxcar function according to our experimental paradigm, and after that we can define the time period for whole experiment, and this function we can convolve with the hemodynamic response function, and we will get a design matrix for our experiment. Here in this slide, we can see the time course simulating a block design of an event-related design experiment. For all the simulated experiments, oxy and deoxy synthetic time courses can be set at any sampling rate, and duration time can be taken according to the experimental time. In this figure, we can see the block design of oxyhemoglobin synthetic data generation, and they set the sampling rate at 1 hertz and the duration was set at 600 seconds. Here we can see they generated the oxyhemoglobin synthetic signals, including a task related component, a noise component, and a physiological task independent component, including the Meyer wave. And for the block design experiment data generation, they firstly generated the task related component as a boxcar function and convolved this boxcar function with the hemodynamic response function. And we can see that in this boxcar function, they took the amplitude to one arbitrary unit during the task period, and they took 0 during the rest period. And they designed the boxcar function including 5 task blocks separated by the rest periods. In previous slide, we saw the block design synthetic data generation, but here we can see the event related design synthetic data generation paradigm. So in similar to the block design synthetic data generation, here we will define the box cars in the seconds form to represent the uh, events in the experimental paradigm, and we can take the value of events as a constant at any particular second according to our experimental paradigm, and we can also define the time course of the experiment, and we can define a hemodynamic response function, and we will convolve the uh, event related boxcar function with the hemodynamic response function to obtain the design matrix. And in this design matrix, we include the noise, Meyer waves, and the hemodynamic signal, oxyhemoglobin signal, and convolving all these signals together, we will get the hemodynamic response signal according to the design we define in the section C. So this is the same procedure we used in the block related design synthetic data generation, and similarly we can also define mixed experiments to generate mixed design synthetic data generation. Here we can see the synthetic data they generated to validate their algorithm. In figure A, we can see the a block design synthetic data they generated. In figure B, we can see the event related synthetic data, and in figure C, we can see the mixed design synthetic data. Like in this, we can see the blocks as well and the events. Uh, Similarly, as they generated the data for the validation of their algorithm, we can also generate the data for experiments and can train the algorithms to enhance the performance, and we can also validate the performance of our algorithms. So this was the information I thought could be beneficial for the listeners. For the listeners, they are working on different deep learning algorithms or something like that. So this is the end of today's presentation. I hope you liked the information, and if you have any question, you can ask in the comments. And thank you for listening me, and have a good day.